Hello, everyone. I am Paul Steffen, and I'm going to be presenting about the Ecological Relative Risk Approach, ECO-RR, an improved alternative to traditional pesticide assessments. Now, let me start by going through the abstract. So basically, what this research is done on is in agriculture, because of the variety of chemicals we have to use, like fungicides, herbicides, pesticides, etc., we have to go through diagnostic decision-making processes to figure out what the toxicity of these chemicals are for our specific environment, or what kind of advantages they can provide. Now, there are a few different methods of doing these tests, and a really popular one is the EIP, and this is the Environmental Impact Score. And it's done mainly because it's fairly simple to use, but it focuses mainly on water contamination. What the ECO-RR does is, instead of having a singular overarching model, it really tests all the different environments or sections that are found on a farm or wherever you want to apply your chemical. And it also includes data like biodiversity, the taxa of the region, and other events like flooding. And it takes all these factors and gives you a relative risk score that the chemical has on your region. Now, this is very innovative because not only can it help farm managers decide on what chemicals they should apply, it also can allow them to extrapolate data, so they could actually make tests for certain chemicals before actually using them, and that could save them money. This could also help researchers, and at the end of the day, it could prevent a lot of ecological damage that farmers sometimes have to do to their surroundings. Okay, so now moving on to the intro. Now, there's a high demand for these new toxicity models because of the ever-expanding agricultural landscape, especially with the need to feed the world's growing population. And naturally, with the expansion of agriculture, we are using lots of chemicals, and we are doing ecological harm. Now, if we could mitigate this, that's great for the environment and also most likely for our wallets. Now, there are some other, I briefly talked about the EIP, which is an environmental impact score, which is used commonly. That is a simple model. Now, other more complex models like the SynOps and the IPEST methods are a bit similar to the ECO-RR, but they are all developing and being tweaked and improving over time. The ECO-RR approach is really holistic and takes into consideration many different variables found. And I'll go into those variables and the methods so you can see exactly how this method is used. But a key takeaway is it really is specific to the desired location you want to make this test for. So you could really test a chemical for your location, not just taking overall data toxicity of that chemical, but rather specific to your area. And the extrapolation of this data can also help prevent or preemptively prevent damages if you have to use a chemical. Okay, so I'm going to get into the methods. So this research was done on a test site of 300 hectares of cotton production, and 37 different pesticides were analyzed with the ECO-RR method. So it was a pretty comprehensive test for this method that was done. Now I'm going to walk through the steps of the EcoRR method. So first, you have to make a exposure calculation. And when doing this, you have to first break down your area into compartments or sections. And those are air, soil, vegetation, groundwater, aquatic water, terrestrial water, and sediment. And you measure each one of these areas with a predicted environmental concentration. And and that stands for PEC, area, and volume. So you use these three pieces of data and you plug them into a formula to get the dose for each compartment. And so let me go over that formula. Dose equals PEC times, in parentheses, volume over area. So this gives you the exposure data for each section. And then after this, after you've obtained the dose, you have to find another piece of data, which is the probability of exposure. And after that, you find the half-life. Lastly, the concentration factor is also determined with a model called the quantitative structure-activity relationships. And once you've gathered all this data, you put it into the exposure formula, exposure being X equals D, which is dose, times P, persistence, times half-life of the chemical, times the bioconcentration factor. So this is the first step, finding exposure. The second step is the toxicity test. So the toxicity test is, first you need to calculate the TGM, which is the taxon LD50 geometric mean, and LD50 is the lethal dose to kill 50% of that species. And because it's not, there are different ways to get the TGM, but it's not practical to get data on each bit of fauna for a specific taxa or taxon. So instead you get, for example, let's say the crustacean taxon. Instead of getting all the different crustaceans of your local area, you could just use a crab that has data already done on it and use that as a surrogate species for the rest of the crustaceans. So this allows people, without having to get so much data from each specific creature in their area, still be able to make these tests. So after you've gotten that piece of data, you have to also find the SI number, which is the number of species in that taxon, and N, the number of species from all the taxa combined. These numbers are then inputted into the ecological toxicity equation, which is right here, as you can see. So you can see the TGM, the taxa, the SI, N, and then over N. And then these are all added together. And then with that, so after you've added all the, let's say, crustacean, the bird, all the different taxa of the region, you get the total toxicity value. Okay, after that, you now are able to find the relative risk of your area. And so with exposure and the ecotoxicity data, you put this into the final formula, which is the equation of relative risk, and you find out each compartment's relative risk. So if you remember all the different compartments that we mentioned earlier, being air, soil, vegetation, water, aquatic, water, terrestrial, groundwater, and sediment, we're going to find the relative risk for each one of these regions. Now, I'll give you an example. So EcoRRA, which would be the ecological relative risk of air, equals exposure over ecological toxicity of that specific area. Once you find this, you'll have the relative risk, and then you could add up all the relative risks of these different compartments, or you can look at them individually. So that's an advantage of the EcoRR. Okay, so now the results of this study were, after testing 37 pesticides, we were able to compare them. If you actually look on this graph, these are the 37 pesticides right here. And they were able to be compared in how toxic they were, or what their relative risk was for the environment, and what risk they posed to which compartments. So on the far left here, we had a very high relative risk of parathion. And if you look closely, the main risk comes from the aquatic compartment. So with that data knowledge, a applicator would, if they had to use parathion, they could prepare and prevent maybe runoff from going into the aquatic environments. And we can see we were able to pinpoint which chemicals were the most toxic, and those were parathion, endosulfan, and chlorpyrifos, which were all above 100 relative risk score, which is a medium risk. And parathion was the only one that was over 400, which is a very high relative risk. So that's very useful information that a applicator could use. Now, also the second chart, the table right below, shows us where the harm came from. So we mentioned that this harm was mainly, let me move my cursor. This harm was mainly found from not the terrestrial water source. The relative risk for parathion from a terrestrial water source was actually less than 0.1. Instead, it was from the aquatic water source, which relative risk of 726. So you can see how important it is to know these, the relative risk of these individual compartments, because with that, you can really calculate and strategize how to protect your ecosystems. In comparison, endosulfan and chlorpyrifos were a little bit more balanced in toxicity to the aquatic and terrestrial water sources. For example, endosulfan had a aquatic relative risk score of 133 and a terrestrial of 58. So not as much divergence compared to parathion. Now, this region was also had commonly floods. It was a wetland. So they wanted to be able to extrapolate the data to find out what would happen to the toxicity levels of these chemicals if there was a flood. And you could see the data right here. The black bars are if there's a flood, and the gray bars are when there was no flood. You could see the relative risk went up significantly if there was a flood. And this is, once again, useful information for if they had to use certain chemicals like prometrin, which actually doubled in relative risk if there's flood. So possibly an applicator, if they knew the flood season or the rainy season was coming, they could choose a different chemical that was less prone to relative risk escalation during flooding. Okay, so now moving on to discussion. The data in this experiment really showed the potential of the EcoRR method. It was able to show a comparison amongst 37 chemicals and really honed in on the ones that were most ecologically damaging or had the highest relative risk to the environment. And this really allows farmers to quickly have a field of vision of which chemicals are going to be damaging and which are not, and what areas these chemicals are going to damage. And having this data, as we find in the modern era, data has become an industry of its own. And it's not with little reason. Data can help immensely with saving money. Farmers won't have to test out the results without any with little information. They could actually run some of these tests themselves or hire someone to do it before buying these chemicals, so they can strategize their seasons, which they're most likely pretty aware of what's going to happen during. And another thing I found vital to this study was something like parathion. Which is a toxic chemical. We were actually able to hone in on which ecological compartment it was most toxic to, which in this case was the aquatic. And this really gives a strong ability to the applicators or the researchers or the chemists to find ways to maybe protect against this damage, or maybe they can create new chemicals that aren't going to be as prone to damage for these aquatic environments. Okay, so now and agriculture environments throughout the world are extraordinarily different, and so this not only does it help the applicator, but this method also helps with the diversity found in agriculture, because it could be used for any specific location. It's not a model that's just like a shotgun approach where it applies to everything, but rather it's a model that is tailored to your exact area. And that is really invaluable. So now I'm going to move on to concluding thoughts on this presentation. The EcoRR method has really demonstrated how effective it could be at testing a variety of chemicals and showing their relative risk with the consideration of many variables like flooding, the biodiversity of the fauna, the terrain of the region. And this really provides an adaptability, and especially in the constantly changing world that we face with life-changing events always happening, global warming, and the expansion of agriculture, which is going to be necessary for the growing world population. Really, methods like EcoRR are going to help, as we expand, it's going to really help us mitigate the damage that we're going to have to do on the environment in order to feed the world. And additionally, right now, this method may be slightly cumbersome, as you may have found when we walked through it. But with technology, maybe we can ease this cumbersome nature of all these equations, and we can integrate this into software that's maybe accessible to everyday farmers. So, as you can see, there is great potential in these methods and their implementation in agriculture. And hopefully you maybe learned a thing or two about the EcoRR method and how it can be used and why it's important. If you want to see, here are my references for my article and my poster. And I hope you enjoyed the presentation. If you have any questions, please let me know. Once again, my name is Paul Stephan, and it was a pleasure. Thank you.